quantum measurement in quantum field theory specifically. And so we've had several talks that touch on those themes, some more directly than others, but I'd just like to open it up. I don't know if any of the people on the panel want to start with their comments. We've seen different approaches to thinking about measurement, both from the philosophical and physical perspective. So I think there's a lot of material for us to dig into.
I'm trying to find it.
Well, I was just going to say, so I was just going to offer a more critical perspective on the talk I gave, right? So I think the research program that I was talking about is very much a work in progress. And so, for example, David was asking about superposition. Like, one of the things I don't really want to say more about the measurement problem right at this moment, because part of like what's the work that's being done right now on the mathematical side is like is getting from the like abstract star algebra that I didn't get out of, right? Everything was at that level, but there's some sort of there's work that needs to be done to first, like they've done a bunch of work on C-star algebras, and then beyond that, like thinking about concrete von Neumann algebras, and that's where you get into questions about type 3 algebras, and then that's where I mean, it's not like they have nothing to say about that, but that's what they're working on right now. So I think I would like to see some of the like concrete examples at that level to start like talking about superposition, say, right? So so anyway, that's just like a critical take on my own talk that relates to some of the things that David was saying. It just like really flag this is really new work that's still going on, right? So so that I think that before we can really engage with it, there's going to have to be elements done.
I'll start off with one more other comment, which is striking to me that there's a whole technology that was developed to try to understand the content of quantum field theories through their scattering amplitudes, right? That took decades to sort of get a handle on exactly how to think about that. And my impression is that one of the things that's going on is that people are wanting to say a lot more about the content of quantum field theory and other kinds of concepts where you're then asking, are there ways, and it's sort of a measurement problem in a different sense. It's more like, how do we imbue the formalism with physical content, not necessarily the philosophical measurement problem, how do we get definite outcomes, but more just, if we have a local system that's interacting with the quantum field, how do we understand the quantitative features of that field and how it's going to couple with a measurement device that we can think of as a locally interacting device. So it seems like an interesting shift in trying to develop that technology. But there's another thing that this was partly prompted by Adam's talk yesterday. And this is, I think, one of the features of philosophers that we often don't think about all the breadth of what's going on in physics. People have been using quantum field theory and condensed matter physics for decades, right? So, and those kinds of techniques in those contexts might be ones that give us a different understanding of measurement that doesn't rely on scattering theory and that sort of thing. So I don't know enough to know how that works out, but that was one thing that I was thinking that there might be, in addition to the context that people are exploring now, other contexts where physicists in a different subfield have sort of resolved these issues or partially resolved them. That's just an open-ended discussion.
So I think Eduardo talked about how like unrooted stuff.
Yeah. So there's one thing. I mean, that was part of the discussion at the end of Marie's talk, right? There's one thing I want to separate, right? There's one thing about the measurement problem as an abstract thing, right? It's how to understand superpositions and how to understand, or you know, if we are believers in the larger Hilbert space church, where well, of course, the experimenter even and the apparatus will be all part of. That may give a lot of satisfaction philosophically, but it's very different from what people go to a quantum optics lab, right? And they do a late quantum eraser, delayed choice experiment, for example, and they want to explain what's going on, and you will hear explanation based on quantum mechanics. And say, well, what's going on here and how, and then you have this discussion between, well, ontic interpretations versus epistemic interpretations about what's going on and so on. Well, there's one thing that you only have the luxury of doing that in non-relativistic quantum mechanics. When you try to use the same constructions to construct, you know, we don't have enough detail on microscopics to actually deal with the experimenter in a larger Hilbert space. We don't have a larger Hilbert space access. We don't have even larger Hilbert space to include oftentimes the full measurement apparatus and the process that ends up with a screen telling you 42 as the result of a measurement, right? So in that sense, is the part of measurement theory that what I'm doing is kind of framed. So in that sense, it's actually very important. Like, well, how can we model the process of obtaining a macroscopic measurement out of a QFT? And by macroscopic measurement, I don't mean that the measurement is coarse-grained. It could be a very microscopic interaction between a particle detector, say, and a quantum field. But the macroscopic, what I mean by the macroscopics is what you publish in the newspaper. We found a new particle. We found surgery. That is the macroscopic that I'm talking about. That relationship, like if somebody finds that information, how should I model that within my theory? Because now obtaining information about the system is not innocent. It's actually the core of things like the delayed choice experiments, right? The fact that you have information about which path affects the interference pattern that you're able to measure statistically. How to incorporate that level of coarse grain in the obtention of information to the theory. I do think this is an important part of an operational measurement theorem. By operational, I mean, being able to use the things that we used to use and work very well in non-relativistic quantum mechanics in QFT. Now, both, I think, the Fürsterberg formalism and the things that we've been doing are aiming to that. The difference, perhaps, is that I find it difficult to connect the Fürsterberg formalism of induced observables with things that are observables in a quantum optics lab. I mean, they may or may not disagree with this. Something with some ongoing discussion, as Doreen says, is still in flow. I do think that having a formalism that is compatible with the nature of a theory. So the main problem that you run into if you try to naively do these kinds of updates is that you start violating on many of those actions, including macrocausality, including the relativistic nature of the theory. When you try to do it, that was Sorkin pointed out, right? There are ways to do it that are consistent with not doing that, and also consistent with connection to what an experiment really is, right? So I think that's important. This is mainly. I would not be discussing what is. I have. In fact, I am. If you ask me, my opinion is indeed, and it was said, right? That my opinion is that there should be something like a larger Hilbert space in which you can actually understand everything on equal footing. There's nothing special about the measurement itself. But we do need, in order to actually connect with the physics that's going on, we need a mechanism that describes the interaction of particle detectors with quantum fields, and the obtention, not only the interaction as a unitary that couples the detector to the quantum field, that we kind of know how to do, but the fact that after doing the experiment, somebody has learned now information about what's going on. That information needs to be included in the description of the dynamical picture of the field. And if two people find information in areas that are space-like separated and then they transmit it to another processing region, that information, the ability that the obtention of that information should be incorporated into the prediction of what other results of other measurements will be, right? And that's mainly, I don't know if that's what you were aiming at with the comment or not. But.
Yeah, no, that's.
Carlo and then David, and then Mark.
I have a comment and a question. The comment is that I would like to dispel a little bit this idea that quantum field theory is only about scattering amplitudes.
Yes.
And I think it's false. Quantum field theory is what, a century, half a century old, and it's used in all sorts of things which are very, very far away from scattering amplitudes. I could list many. I think David probably could list many more than me. I've been in laboratory in Paris where there is a cavity and people measure the energy in a region and find the quantization not of the particle number but the energy in a finite region and the states. QCD, there are calculations of the hadron masses. Theoretically, if you think, I don't know, UNO calculation of what the detector would see, it's just quantum field theoretical calculation entirely. I mean, one can go on and on and on. So it's much, much more than quantum field theory than scattering amplitude seems to me. This is not to dismiss this, it's not at all, but there is all that. And many of the things that one measures are local in various cases. Even at CERN, the calorimeters that measure the energy in a region are sometimes clearly focused local measurement. And even the CERN particles are not the particles of the scattering amplitude and have been analyzed as such, because they're measured by local things. The scattering particles are, the Poincare invariant particles are the local object. So that's what I wanted to having said all that, you started with the Sorkin thing. This Sorkin thing has been measured, has been mentioned repeatedly. So that's my question. What is the actual solution of the Sorkin problem?
Okay. So, so in response to the first thing, I also don't want to give the impression that quantum field theory hasn't been used for systems in the world that even that we think that we're using the theory to measure what's going on in an approximately local way. So I think actually part of what I was thinking about that's important to mention here is there's this whole line of development of like RQI thinking about unrooted width detectors, right, for example. And so I think that's an important input into the kinds of things that Eduardo's thinking about. And so yeah, that's one of the examples he gave, and I think that's one place where it's not like there's only work that's happened in the last few years and then nothing has been done before that. So yes, I totally agree with that point. What about the Sorkin problem? I think that would be so that's like a different piece of the puzzle that I gestured at. So one thing I will say is that there's Sorkin's original paper from 1993, which involves global hypersurfaces. There's an updated version. There's a more precise version of it, which is the one that actually is become important now by Worston, Jubb, and Cowles are the three authors on the yeah. So I think and that's the one I had up there with the three local regions. So I think there's a lot more to be said about what exactly the assumptions are that go into it, but it's not full quantum field theory. It's like microcausality plus assumptions from non-relativistic quantum theory. Then you use Luder's rule and you for non-selective measurements and then you run into problems. So that's the two brief description. We're going to have more to say about this.
So the problem comes from the fact that one import a non-relativistic approximation within relativistic theory and one sees is that what?
So I think one way of thinking
of
about that problem as a kind of reductio argument of that very simple setup for dealing with relativistic quantum theory, then the beauty of that is you can see, you ask what the solution is, there's not just one solution. You can approach it in different ways, and that's what I was trying to gesture at when I had the bunch of different approaches. One thing you could do is double down and say, look, I'm just going to keep using Luder's rule, and I'm just going to regard any observable that turns out in this framework to signal as being unphysical. So that's been done. That would be one approach you could take, which keeps Luder's rule. One way you can see the FD framework is as coming up with a new set of state update rules that's appropriate for QFT. Those are two examples, but there's not just one solution to the problem. It's here's a bunch of assumptions that seem to be in tension, assuming we don't want signaling to happen, superluminal signaling to happen. And so then that's a starting point for different research programs.
There should be a physical story to tell, not just...
Eduardo, yeah.
There's one thing, something you mentioned that everyone said, the impossible measurement problem is not coming from approximations. It's just, okay, now I want to be able to measure my fully covariant and relativistic observables in the theory, no approximations made. How do I model the update rule after making a measurement and obtaining information? Now, what Sorkin was pointing out, and more modernly, this paper called Impossible Measurements Revisited, is that, well, you want to model this with update rules that come from projective measurements, even of, again, the spectrum of those operators, no approximations made, spectrum of these local elements of the algebras of observable, elements of the local algebras of observables, then you enable superluminal signaling. And then they basically, in that paper, it's actually really nice because they identify the kind of operations of update rule that are okay and the ones that are not. And the most, I don't want to call it naive, not naive, but the most direct ones, the ones that you would import from the philosophy from, not philosophy in the technical terms, spirit of non-relativistic quantum mechanics, those fail. Those are not within those sets. But no approximation is made. It's basically selecting what kind of update rules are okay with the relativistic causality of the theory. And they identify that many of them, in fact, the ones that everybody would use if you ask somebody who knows QFT and knows quantum mechanics and said, now in QFT, try to do a state update. How would you do it? I measured the amplitude of the field here, like this quantum optics laboratory you were. They measure the expectation value of the number operator here, or measure the statistics, all the moments of the number operator in this region. Please update the quantum field. And in this paper, Borsten, Jeb, and Kell would say, well, actually, the naive way that you would get from quantum mechanics, as in, like, well, what about a project over the spectrum of this operator? But no, that's not okay. That is incompetent. That enables signals. Yes.
So, and I also put like, so this is the right.
Yeah.
Could you read the, because it's hard to see from
Yeah, sorry. Okay, so this says Borsten, Jubb, and Kells impossible measurements. So that's the.
It's called impossible measurements revisited.
Revisited. Yes. Is that the full name? Anyway,
I think
so
so.
Those three authors. Ian Jubb has a follow-up paper, which I cited in my talk, which looks into what happens if you do the route I was talking about, where you just like keep Luther's rule and then just rule out everything. You rule out a lot, even in scalar field theories. Turns out that maybe is not the right way to go. But then there's this paper by Eduardo and students, a detector-based measurement theory. So this is the like Eduardo's counterpart to the thing I presented today, which is based on certain things you can say.
Okay, so David, and then I have Wayne and the
Okay, so this is sort of picking up on something Carlo was saying. I mean, yeah, we've been using, and I don't take this as a disagreement in this project, I should say, but we've been using QFT since its inception to do non-scattering things. I mean, the lamp shift and magnetic mode of the electron are just classic QED examples and non scattering examples, and we keep using it.
Yeah, almost like
And we don't need a measurement theory to analyze those applications. All we need is the Born rule. I mean, we're not even that for some of those cases. We just need the ability to translate claims about various features of the quantum state into probabilities. The place we need a measurement theory is where we might want to be making measurements sequentially. Even then, we don't need a measurement theory if we're in a decoherent regime where the probability calculus works fine diachronically, even without some kind of Luther's time rule. So if we want to use non-equilibrium QED to study a phase transition as a dynamical process, there's no problem using just using Born rule to do that because everything's decoherent. There's a rather specific, increasingly practically important context of quantum information type iterated measurement protocols where we importantly need to think through a measurement theory, and where the sort of church of the larger Hilbert space move is difficult to do in practice, so we're trying to find ways around it. But I wouldn't want to conflate that with the broader question of how we get predictive content out of QFT outside the scattering regime.
So I think maybe the way I use the word scattering is confusing here, right? So I think you need to distinguish between the theory, like the model that you're using, and using like scattering type constructions in your model, and then how you're using that to describe things in the world, right? So we call scattering processes in the world and scattering in the model. So yes, I totally agree that you can use that way of setting things up, and the other ways you describe, David, to describe all sorts of things, right? But that are not scattering in the world type of applications.
But they're not scattering at all. I mean,
yes, exactly, yeah.
I mean, you could debate something like the lamp shift, but something like non-equilibrium QED or transport phenomena in neutron matter, those just aren't remotely scattering applications.
Yeah, I probably have other things to say about that, but yeah.
Good, I think that's helpful to draw a contrast between the sequential measurement cases and something where you really have a measurement theory in some more refined sense than just understanding some probability.
One comment on this. I basically would say I could sign on what you said. There's one thing that I want to just highlight, perhaps not to simplify it. I agree with you in everything you said, but you see, sometimes you have to do measurements that are not time orderable, and that's important for some protocols, right? For example, you have space-like separated measurements, and it is important that they are space separated for even the interpretation of what's going on, and sequential measurements that are space-like separated with processing measurements that happen in a region you can signal both. In that sense, and again, from the perspective of relativistic quantum information, or even understanding how much about some basic tenets of quantity, for example, if you talk about the entanglement structure of the vacuum, right? In order to acknowledge those, in order to make experiments and actually be able to measure these kinds of things, for example, entanglement in the ground state of a QFT or things like those, you need to have a way to incorporate the sequential measurements. And sequential is, I wanted to pick on that word, right? Because it could be non-time orderable, so what's sequential mean here, right? And that's why this formalism, I feel, is very important in that sense.
Yes, multiple measurements where the
Yeah.
very idea of
All
order
in
is
one
simultaneous
protocol,
in relativistic theory. Yeah, good.
So Noel had a comment on this, and then
Yeah, I just wanted, because I know we're trying to like isolate some of the sort of distinctive challenges for measurement and measurement theory in QFT, and like on this question of when we use sequential measurements, there's a general thought of, well, we want this sort of nice pairing between like CP instruments and measurement schemes that we have in non-relativistic quantum mechanics. And figuring out how to do that in something like a general quantum field theory is hard. And like two very specific reasons why it might be hard. One is that like the repeatability, like standard like fundamental repeatability hypothesis fails for continuous observables. So there's one sort of, how do we do this kind of thing for continuous observables? That was taken care of in the 80s. Then there's a second problem, which is that the standard proof that you have kind of a nice one-to-one correspondence between CP instruments and measurement schemes relies on background assumptions about type 1 algorithms. So if you're in like an AQFT where the local algorithms are type 3, there's no obvious recovery of that. But one thing that has been done recently is a sort of generalized proof of that. So this Uzawa and Okamura have a way of doing using essentially the fact that the local algebra is not just type 3, but type 3 1s are objective. You can have funnels of type 1 algebras and use that to approximate PWM. So essentially you have a nice one-to-one correspondence between a certain class of special extendable CP instruments and measurement schemes in that context, which is cool.
okay. Wayne?
Again, my question is whether the panelists would agree with the statement I'm about to make. Right? It seems to me that what in a lot of these discussions, we're running up against the old traditional measurement problem, and some of the things that are being said, you can ask, well, what does that mean? And there isn't going to be an answer to it that's neutral with respect to approaches to the traditional measurement problem. And let me just explain what I mean by that. So, like in Dorit's talk, in this piece of formalism, you have these conditional probabilities or conditional expectation values, and you might ask, well, okay, what do those mean? And if we update the state, is that a physical process or a calculational tool? And then Eduardo was saying, okay, how do we represent it within the theory when someone gets a piece of information? And it seems to me that both of those things, you're going to say different things about what they mean depending on your approach to the measurement problem. So if you're an Everettian, those conditional probabilities are easy to make sense of, right? So if I'm an Everettian agent, I've seen this result of the experiment, then I'm going to use these conditional probabilities for experiments to my future, and I might even apply a state update rule with the idea that this state is local to my branch and it's not a global kind of thing, and that state is going to be fine for future experiments, as long as no one's going to come in and do a weird experiment that exhibits interference between branches. Okay, and Eduardo's thing about you get the information that you saw something. Well, in an Everettian context, each agent is going to see, okay, what I've learned is I'm on a branch in which this result is obtained, and there might be other branches where. Now, if you mean that the agent gets the information that this is the unique result, then I think we're beyond. If you're in a single world context, then you're either in a situation where you've got some kind of hidden variable theory, where there's extra structure beside the quantum state, or you've got some kind of collapse. And there's been talk within the literature on how to interpret collapse theories about how you update states. How do you make sense in a relative to the context of collapsing, non-unitary evolving states? And the thing that has become pretty much the consensus is a sort of modification of the Tominaga-Springer picture. Again, the old Tominaga-Springer picture, which was unitary only quantum mechanics, quantum field theory, you associate a state with any space like hypersurface. And in the collapse context, the natural thing to do is do exactly that, and the state associated with a space like hypersurface is conditional on probability, gives you probabilities of events in the future, conditional on collapses in the past. And it seems to me that I'd have to sit down and look through that. But from the sounds of it, that sort of thing could be a state update rule in the Fuster first framework. So I guess so the question is it right? Are we bumping? Do you agree that we are in fact bumping against the traditional measurement problem? That some of the things that are being said aren't going to have the question, the meaning of what's being said isn't going to be something that's neutral with respect to approaches. And David has a finger, but we'll work at that. Responses.
So I definitely agree that in many cases we're trying to have ontological discussions about
Again, could you speak up a little bit?
I definitely agree that in many cases, particularly if you're trying to sort of say something about ontology in QFT, it seems very hard to make much progress without some interpretation in mind. But I do think it should be a two-way conversation, right? I think that, as I sort of spoke about in my talk, I do think that QFT can help inform your ideas about how the measurement problem should be solved. And so you shouldn't necessarily say we shouldn't have those conversations at all until we know the solution to the measurement problem, because maybe we have to think about QFT in the first place just to help figure out the measurement problem. So I think that the two need to inform each other rather than it being sort of one-way thing.
Does anybody else on the panel want to speak?
Did you want to say that?
Go ahead.
Well, I'm not sure that the measurement problem in quantum theory. Okay, so in the formalism that I discussed, I don't think that there is some kind of sheet on how to solve the measurement problem in quantum theory. Yes, so I think in quantum theory, but I think I agree that you need to have more technical advances and then discuss more on this. And apparently it's related to the problem of non-relativistic quantum mechanics, but it's hard to. So it should be, the solution should be related, but see.
I was just going to agree with the part of what you said about even once we've figured out fully, say, what's going on in the FE framework, you're going to have different interpretations of that framework, and it's not. I mean, we wouldn't expect the math to fix one particular interpretation. I do think, though, in line with Emily's talk, that there are going to be interpretations that were viable in non-relativistic quantum mechanics that people have tried to extend to quantum field theory that are not going to be viable anymore, right? So I think actually the Schwinger-Tominaga one I'd be worried about. But again, in order to be able to say something definite, I think we need to get to the point of having some of the rest of some of the things that Noel was talking about too, filled in. So the condition, and so I wanted to be clear that I was not adopting an epistemic interpretation of the probabilities. I tried to give a different interpretation of the states, but I think there's going to be different ways to go there, for example. And so one way of explaining what needs to be done still is I was doing conditioning on the probe effects, right? I was not conditioning on on the value system observables, right, and what values they had. That's the kind of thing you want to do if you want to give an interpretation. That's related to what Noel was talking about, some of the tricky parts that are being figured out.
Okay, so maybe one thing I would say, I basically agree with what you said. This command is both Firsterberg and what we don't do. It's relatively agnostic on the interpretation. However, I would say, and this is something, while outside of this is an opinion point here, I think that if you ask me, at least for what I've done, what I can talk about, it's definitely friendlier with a more Everettian way of seeing things than it would be from any collapse way of seeing things. Because, for example, the update rules that are derived, for example, in the detector maze ones are contextual to seek to, for example, update rules on the causal future of where the measurements are made, provided the information is transmitted. So the rules are definitely context dependent, and it's much easier to make sense, in my opinion, from an interpretational point of view, from an Everettian point of view, than a collapse-driven point of view. However, this is opinion, and I'm not a philosopher.
So I would say, having read more of your stuff, that the epistemic interpretation of probability, however, is very important to the way everything works out. So I would qualify the Everettianism. I guess it's not collapse; it's unitary-ish. But then, like what you say beyond that, I think is more like maybe relational.
Well, maybe relational is better. You're right.
Yeah,
You're
then,
very right
or
in that. Yes.
But
certainly not.
That was for the philosophers.
Fair
I
enough.
didn't want David to run away and write down.
I see. Thank you.
Yeah, I mean, picking up back to Wayne's point, I mean, I think there might be less interpretation dependence here than you might think. I mean, if one has an Everettian reading of this, like I'd want to, and instead, if one, I mean, neutralism about that many worlds. If one just has a church, the larger Hilbert space, do everything unitarily way of thinking, then collapse is going to be an effective description of subsystem goings on. It doesn't need to be taken too literally. And in particular, I think, as far as I can see, it would be totally harmless from a larger Hilbert space starting point if one's effective collapse theory was variation dependent. Provided I didn't have any actual disagreement on empirical predictions, then variation dependence would be totally harmless. And I'd probably expect it from an Everettian point of view, because collapse is kind of very related there to the decomposition into branches, and if I've got space-like separated goings on, then there's going to be an element of convention and probably foliation selection in stitching together branches in space-like separated regions. If you're doing a collapse theory and collapse isn't just a convenient, effective description of something fundamental, then of course you're going to interpret that differently, and you might worry in a collapse theory whether foliation dependence is a problem, but if you've made your peace with foliation dependence, then of course that's just going to be fundamentally what's going on. So I wonder if that actually, is it going to make as much difference as you think?
Okay, so you're using this phrase foliation dependence, and I'm imagining fully relativistic quantum collapse theories that are not foliation dependent. So
I mean surface dependent. I mean
states are states on hypersurfaces, but that's just okay. I can't think of any other way of having evolving states in a relativistic quantum.
That's the point.
Right, in relativistic. So I mean, in Galilean space-time, so state in the Schrödinger picture or something, states are time dependent, right? For it, in Galilean space-time, for any space-like hypersurface, you've got a state, and they're different on different space-like hypersurfaces. You just say the same thing in the Minkowski space-time or other globally hyperbolic.
Yeah, I mean, as you know, the problem is going to be I'm going to have surfaces which coincide in a subregion, but where the reduced state of that subregion isn't the same on two.
Okay, yeah, so that's a problem. Yeah, so this is something that I think really, I know there's other people. This is something that I think causes a lot of confusion when trying to understand collapse theories in relativistic space-time. The idea that you should be able to take a hypersurface, look at a subregion, and think of the reduced state on that that subregion as a local beable or as something intrinsic to that, and it's not.
If you have
it's not. It's a reduced state that comes from a global state on some hypersurface. It's not a local beable.
Well, hang on, that's collapse theory dependent. It's fine as a local beable in a unitary theory.
Well, yeah, right. But in the collapse theory, you have, well, I would still say it's not a local beable, but it happens to be the same thing from.
Not a local vehicle, but has the same value in a local region in respect to capability.
Yeah, exactly.
I'm happy with that as a local vehicle.
Right. Yeah. But yeah, like almost all the confusion comes from thinking, okay, the reduced state of a region has to be a local intrinsic thing. About that.
I was trying to be conciliatory, and I got distracted into the issues of collapse. The point I was going to make is if what I want is a dynamical description of collapse, whether fundamental or effective, but dynamics is defined on foliation, and I can have compatibility with lots of different dynamics in a relativistic theory, and I might have Adler-esque concerns or something wrong about that framework, but insofar as I'm doing dynamics, I'm picking a variation, I'm describing on that. And I'm going to have a different, I might well have a different collapse story, whether the collapse is fundamental or effective. I can perfectly happily have a different collapse story described on a different variation, and that would be harmless, I think. So it's certainly harmless if collapse is only effective, and modulo collapse theories addressing their metaphysics in a satisfactory way, harmless on collapse theory as well.
Okay, I think Carlo had a finger on this.
My first class in quantum field theory, my teacher started by saying, all right guys, forget the Schrödinger picture, from now on is Heisenberg picture forever. When I started going to quantum gravity, it was obvious to everybody that the Schrödinger picture doesn't work. The Schrödinger picture has a picture equivalent in non-relativistic quantum mechanics. Obviously, we know how to go from one to the other. Outside non-relativistic quantum mechanics, the argument of the connection of the two fails. So one survives, one doesn't. And I've always been told by my teachers that the one survived is the Heisenberg picture. Dirac gave his last talk in Erice, in Italy, with one single slide, which was the commutator of A and H, whatever, and one single line, which is the Heisenberg picture is the right one. So I got completely used to the idea that if you try to import Schrödinger picture notions, I mean, for sure into quantum gravity, which just doesn't mean anything, but forget quantum gravity, which is not what we're talking about. In relativistic field theory, you just get confused forever because it's not the proper. Well, that's what I want to offer here. So it seems to me that a lot of the confusion comes from this idea of willing to import a logic which is just extraneous to Lorentz invariant field theory, Lorentz invariant physics.
Yeah, go ahead, Wayne.
Yeah, and that caused me a lot of confusion too, about how to think of the equivalent of a Schrödinger picture in relativistic quantum theory. And that's because the Tomonaga-Schwinger picture just totally dropped out of the textbooks after the 1950s. Like it's there in Schwaber's textbook, but later than that. But once you start thinking, okay, now I want to have collapses as a physical process, you want to have evolving states, then you have to think, okay, maybe that was a mistake that dropped out.
Oh, yeah.
So I'm going to say the opposite, Wayne, and say
somebody else realizes, well, let's not think collapses.
What's that?
Yeah, a part of the community react to the same tension by saying that's a good argument against collapses in physical.
Right.
Yeah. So Carlo, I was going to say that was like in my end slides where I was explaining so part of the original operational interpretation of AQFT was a Heisenberg picture, but that actually doesn't even fit with that piece. That doesn't even fit with AQFT before you consider measurement. After you consider measurement, then that kind of idea that there's a Heisenberg picture in the sense that there's a unitary dynamics over time slices, that it's the observables that are evolving, that doesn't make any sense, because the way I think of it is, in the algebraic approach, the way you specify the dynamics is initially on bounded regions, right? It has not, and you could recover the time slices if you want, if you pick a foliation. But fundamentally, already when you've assigned the algebras to the bounded regions, then you've specified the dynamics on your spacetime. So it's Heisenberg in that sense, that it's the observables and not the states that are carrying the dynamics, but it's not a unitary dynamics. Right? It's not a state evolution view over time.
Noel, you had a comment a while back.
Oh, I didn't have a comment. I had a question too.
Sure, a question.
Yeah. Well, now I'm tempted to talk about Schrödinger stuff, but I'll steer in a different direction just for the sake of variety. So here's like a puzzle that I've always sort of wondered about related to measurement in quantum field theory. There seems to be kind of prima facie a tension between, if you look back at like old podcasts or QFT stuff, sort of what they say about measurement, which is it has to be localized, and the observables are operations that are assigned to compact regions. And then all these results seem to indicate that particle-like structures have exponential tails. So particles are not local in the nice sense we might hope, right? They're not compactly localized. But if we're thinking of, the things we're measuring are oscillations in the quantum field, and the things we're measuring them with are composed of oscillations in the quantum field, and we're composed of oscillations in the quantum field, what we have is apparently a bunch of interactions between non-local stuff, but we're still then requiring some kind of sharp locality constraints where the observables are assigned to sharp bounded regions. And I always wondered, like, it seems like there needs to be slippage somewhere. I'm not sure where the slippage should go.
If you ask me, I think that particle descriptions are really bad, and that physics is local. As in, like, physics happens during a finite lifetime in a finite extension lab, and what people are doing in Australia right now does not influence that much what we're doing, right? So I think that the picture, not surprisingly, right, you can write something localized as a linear combination of things that are non-localized, right? That's what happens. I feel that our minds were very used, our minds, not ours here, right? I think that's pretty much clear. But that people historically, it's very easy to think have intuition in terms of particles, things that, have a definite position, different momentum, even if approximately. And then exporting that is what gives rise to this, like the fact that we use a lot of non-localized objects to model everything. Even the hydrogen atom is infinitely localized, right? Where in reality, right, we are localized beings. And certainly, I think local physics is what matters, right? So I would say in particular there's no tension other than, there's this paper by Lamb, a really nice paper, it's called Anti-Photon. That abstract I always use when I give a talk to students, because it says, I want to argue that we should stop using the word photon, and then he actually says, only a comedy of errors and historical misunderstandings have led to its popularity among physicists and opticians, and it's funny because we don't need to use that. So he at the end says the key is like, well, objects that are, for example, very massive objects like hydrogen atoms or electrons. All those things you can think of them in terms of particles more easily because they have a well-defined non-relativistic and non-quantum limit in a way. But the moment you want to put the two things together, you have to abandon the notion of particle because of that, like problems of locality, right? So my opinion is that there's no real tension other than we should probably, at least from it's an inconvenient fiction. It's a convenient fiction, let's say. You're talking about particles helps us many times get intuition, but it's certainly not, I think, the way we should be talking even to the general public about quantum fields. And I do think that it's important. Localization in time and space is important. Local physics is important, in my opinion.
So I think this is provoked both David and Carlos.
This is completely to agree. It remains the fact that if you have a screen and a weak electromagnetic wave that arrives, the screen, there are dots that come in. This remains. So that's a sense in which photons are photons.
Yeah, and in the approximate sense, in a way, yeah.
Well, I mean, I'm sympathetic to a lot of this, but I mean, it seems possible, insofar as real processes are exactly local, that the right way to define measurements is such that real processes don't exactly manage to be measurements. I mean, plausibly, the things that end up being defined have in a clean, sharp way have exponential tails. And then we'd just be saying that the actual genuinely local processes are not exactly those, but exponentials disappear pretty quickly, so it's close enough for government work. And then we see this all over non-relativistic quantum mechanics already. I mean, yes, there are exactly localizable states of non-relativistic particles, but they're unphysical. They spread out instantaneously. They can't be confined by finite potentials. And so all of our various physical high-level concepts in non-relativistic physics, technically speaking, have exponential tails. I'm happy to suppose that real processes, even in that regime, are local processes, but I don't see any obvious reason why there should be a perfectly local description I can get, rather than just saying, well, the actual goings-on are really well approximated by this really nearly local, but not quite local thing, and that's the most I can say.
I would have nothing against it, so it is
logically consistent. Don't take that as a contradiction.
And you use Gaussian experiments all the time.
I use Gaussian experiments all the time.
Okay, well, I think this will be an appropriate point to end the panel. So thank everyone for the talks this morning.